Hi, this is Dr. Shaw, and welcome to the beginning of our exam review. This is going to be the material I was going to go over on Monday. I'm going to start with a list of topics. The list of topics is available on e-learning under the handouts folder, but I'm just going to speak really briefly now. The sections are going to be 4.1, using first and second derivatives, 4.2, optimization, 4.3, optimization and modeling, 4.4, families of functions and modeling, 4.7, L'Hopital's rule, growth and dominance, 4.8, parametric equations. If you want to think about this by topic, we've covered like 5 basic things. Derivatives and shapes of curves, which is using first and second derivatives to determine if a function is increasing, decreasing, concave up, concave down, and where that's happening, finding local and global maxes and mins, and finding points of inflection. Then we did the optimization problems. These were the applied problems that I kind of spread out throughout all the homework. Then families of functions. What did you do for them? We determined the effect of varying parameters on a family of functions. This was mostly a calculator exercise. We determined properties of a family of functions, such as where it's increasing, decreasing, concave up, concave down, where its critical points or local extrema are. So the same as regular functions, but now we're dealing with a family, so your answer will have letters in it. And then determining the value of parameters given information about a function. Then we talked about computing limits with L'Hopital's rule, or just directly substituting, when can you and when can't you. And then we talked about parametric equations, sketching the parametric curves. Again, that's more of a calculator thing, determining the speed of a particle on a parametric curve, finding the equation of a line tangent to a parametric curve. And then we kind of got into circles and ellipses specifically there. Cool. So we're going to start by reviewing derivatives and shapes of curves. We're going to look at the witch of Agnesi. Okay. I will remind you of what the function is. That's going to be f of x equals 1 over 1 plus x squared. And we're going to look at it on the interval from -3 to 4. So here's a picture of what we're looking at. And to start with, let's look at the local max and mins of the witch of Agnesi. Now, if you look at the picture, you're probably already guessing that there's going to be one local max and no local mins. But we'll do the calculus and show you the process. So here's our function. Now to find local max and local min, what we want to do is we have to find the critical points, and we do that by taking the derivative and finding out where it's 0 or undefined. To take the derivative of this, we could write it like this. And now use the power rule and the chain rule. So that's -1 plus x squared to the -2 times the derivative of that, which is 2x. And I get -2x over 1 plus x squared squared. What if you didn't think of that? Well, you could also use the quotient rule. So I'll take the derivative now using the quotient rule. It's the denominator times the derivative of the numerator, 0, minus the numerator times the derivative of the denominator over the denominator squared. So either way you get the derivative is that thing. Now the critical points are going to be where this is 0 or undefined. Well, it's defined everywhere, and it's 0 when x equals 0. So my critical point is x equals 0. That's where this thing is equal to 0. Just to remind us, I have f of x equals 1 over 1 plus x squared, and f prime of x is -2x over 1 plus x squared squared. And I've been asking you to put a little box around the derivative. Okay. So my critical point is x equals 0. Now I have to classify it as a local max or a local min. So I draw a number line. I put my critical point here. I write f prime is 0 here. Now, To the right of 0, if I plug in a number, let's say 1, the derivative is negative. You can do that just by plugging it in or looking at it. To the left of 0, let's say plug -1 into this, I get a positive number. And so I'm increasing and then decreasing. That means x equals 0 is my local max. X equals 0 is my local max. Now let's talk about global maxes and mins. So for the globals, you don't have to do the number line thing. You're going to come up with your candidates, which is your critical points and your endpoints. You plug them into your original function. And then whichever is the biggest is the max, whichever is smallest is the min. So let's find out, where is the curve f of x equals 1 over 1 plus x squared? What are the global extrema, the global max and the global min, on the interval we're interested in, which is -3 to 4. Okay, so let's look there. So we want to find candidates, which are the critical points at the end and the endpoints. So f of x is equal to 1 over 1 plus x squared. We take the derivative. I'm not going to put you through that again. F prime of x equals -2x over 1 plus x squared squared. My critical point is x equals 0 because of the same thing we did before. And my endpoints are x equals -3 and x equals 4. Okay, here's my derivative. I'm going to make a table of values, plugging them into the original function. The global is crude. I don't care what's happening, increasing. I just want to know what's the biggest and what's the smallest. So x0, -3, and 4 are my candidates. When I plug 0 into my original function, I get 1. When I plug -3 into here, I get 1 over 10. And when I plug 4 into here, I get 1 over 17. So that's the biggest, that's my max. And that's the smallest, and that's my min. And I should write global min, global max. Okay, so we've looked at how to find we've reviewed how to find a local min and a local max, a global min and a global max. Now let's look at points of inflection. And we're going to just use the same curve and try to find the points of inflection. If you look at the picture again, well, I'm going to attempt to point in the right direction. Yeah. If you look at the picture again, there should be 2 points of inflection there. You see them, right? We're going concave up, concave down, and concave up. So let's find the points of inflection. So we start with, we need to find the second derivative for possible points of inflection. F of x equals 1 over 1 plus x squared. F prime of x is -2x over 1 plus x squared squared. But now we need to find the second derivative, the double prime. So that's going to be, I'm taking the derivative of this now, the denominator times the derivative of the numerator, which is -2, minus the numerator, -2x, minus that, so that's plus, times the derivative of the denominator, which is 2, 1 plus x squared, times its derivative, 2x, all over the denominator squared. So that becomes to the 4th. Yeah. Okay. We get a little lucky in that I can cancel one. I could cancel a 1 plus x squared from everywhere. Okay. I'm trying to do the autofocus and it's just not being as sharp as I want it to be. But I'm rarely as sharp as I want to be. Okay, there we go. So we'll kill one of those. We'll kill one of those. We'll kill one of those. And so what I have left is negative 2x squared plus 8x squared is 6x squared. And then minus 2 times 1 is minus 2. So this is what I get. Like that. Okay. So my possible points of inflection are where this is equal to 0 or undefined. Well, this is always defined because the bottom is never 0. So this is always defined. So where is the second derivative equal to 0? F double prime of x equals 0 when 6x squared minus 2 equals 0, 6x squared equals 2, x squared equals 1/3, x equals plus or minus 1 over the square root of 3. And now we make our handy dandy number line. This is 1 over square root of 3. This is negative 1 over square root of 3. And we need to figure out what's happening with the second derivative for concavity. When x is large and negative, I get a positive number on top and a positive number on bottom. When x is 0, that's in between these, this is going to be negative 2 over 1, which is negative. And when x is large and positive, or if you hate me doing that, you can add like 10 into here and just see what you get. You get positive. And you'll notice I'm looking for changes in concavity, up to down, down to up. So 1 over square root of 3 and negative 1 over square root of 3 are both inflection points. Those are my two inflection points. The next question is, where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? Well, it's exactly the same work. We've already done this work. So let's look at the second derivative. I'm concave up here. I'm concave up here to the left of negative 1 over square root of 3. I'm concave down. I'm concave up. So when you do the number lines, that's also answering the question, when is it increasing, decreasing, concave up, and concave down? So we've just talked about derivatives and shapes of curves. Let's do one more topic now. We'll do the rest on Wednesday. I know it's kind of tough to watch a long math video. Let's talk about families of functions. Okay, so a family of functions is a function that has one or more parameters in it. So sticking with the Witch of Agnesi theme, let's look at this family of functions. F of x equals 1 over x squared plus a. 1 over x squared plus a. So the first thing I could ask is, what does a do? This is a qualitative thing. We're not looking for a number. We're just looking for a sentence. What effect does a have? So what we're going to do is graph this for various values of a. Okay, you can do this on your calculator. I use Desmos. You won't be able to use Desmos on the exam, unfortunately. So here's the curve for a equals 1, a equals 2, a equals 3. And it's getting kind of hard to tell what's going. So I'm going to go back the other way. A equals 1/2. So what I see is that the larger the a, the lower the maximum and the flatter the graph. Aha, though, I've only used positive values of a. Look at a equals 0. A equals 0 is the same as the graph of 1 over x squared. So that has a vertical asymptote at 0. So at a equals 0, the pattern goes away. Now it's something completely different. Now, what about when a is negative? We have to do that. Well, let's experiment. So this is a equals negative 1. A equals negative 2. A equals negative 3. And let's play with a equals negative 1/2. So these curves come in 3 pieces. A thing to the left, a thing to the right. Both of those have horizontal asymptotes at 0. Then there are these two vertical asymptotes and this hump in the middle below them. So what does varying A do? As A gets more and more negative, we can see that the middle lump gets higher and broader. Okay, so that's what it is when we're trying to just describe what a parameter does. You just plug in different values of the parameter and observe. The next thing we can do is we can try to do calculus on these things. So for example, here's a question. Let f of x equal 1 over x squared plus a. What are the inflection points? What are the inflection points? Now my answer is going to have an a in it. So here's f of x. I hate how big my hand is on this thing. And then we take the second derivative. I'm not going to make you watch the whole process. It's basically the same as what we did before, only this time there is an a in it, and we're going to treat a just like a constant. And what we wind up getting is 6x squared minus 2a over a plus x squared cubed. Now, if I let a equal 1, that would be the problem we did before, and then this would be our same value for the second derivative. Ooh, I just bumped that. Sorry. Hope I didn't make anybody car sick. Okay. It's all twisted now. All right, there we are. All right, so how do we find the inflection points? Well, set equal to 0, because the bottom has to be positive, right? And so I get 6x squared minus 2a equals 0. 6x squared equals 2a. X squared equals 2a over 3. I'm sorry, a over 3. X equals plus or minus the square root of a over 3. Okay. There is a problem with what I did, though. This is assuming a is positive. If a is negative, that isn't going to happen. Okay. Sometimes on the homework or an exam, I'll say, okay, assume A is positive, but this time I didn't. So A could be negative. And as we've seen, things are different when A is negative. There's still inflection going on because in the negative case, we're concave up, concave down, and then concave up again. So there is inflection going on, but it's just different when A is negative. So let's look at what's happening when A is negative. So this is A is positive. For A is negative, I still have f of x equals 1 over x squared plus a. F double prime of x is 6x squared minus 2a over a plus x squared cubed. So what's the difference now? Well, if a is negative, this is going to be positive. So the top is not going to be 0. But the bottom can be. So if a is negative, you're going to be undefined when this is 0. And remember, the possible points of our inflection are where the second derivative is 0 or undefined. So that's a plus x squared cubed equals 0. A plus x squared equals 0. X squared equals negative a. X equals plus or minus the square root of negative a. And if this looks weird to you, it looks weird to me, but remember, a is negative. So if a is negative 6, then this is plus or minus the square root of positive 6. And that's okay. So if you're asked any of the standard calculus questions, maxes, mins, inflection points with a family of functions, you use the same exact steps, only that parameter, which is going to look like a letter, is there. You treat it like a constant when you take your derivatives. And then you just have to go through the same process. And it's a little tough because it isn't an actual number. Okay, the third thing we can do is we can find the value of the parameter. We had some homework questions like this. So the idea here is this. I give you a family of functions. I give you some extra information, and you find the value of the parameter. All right, let's do an example of that. Let's stick with our same function. F of x equals 1 over x squared plus a. The same function. But now let's say I want to find the value of a such that f prime of 3 is negative 1/6. So I have this family of functions. I know that f prime of 3 is negative 1/6, and I want to find a. So I'm going to write that here. F prime of 3 equals negative 1/6. Well, I know f prime of x. I would have to take the derivative here. And trust me, you get negative 2x over a plus x squared squared. We do exactly the same thing we did before. And now I know that f prime of 3 is negative 1/6. So f prime of 3 equals negative 6 over a plus 9 squared. So what I did there was I let x equal 3. And I want that to equal negative 1/6. So I get 36 equals a plus 9 squared. So if I take the square root of both sides, I get plus or minus 6 equals a plus 9. So a plus 9 equals 6, or a plus 9 equals negative 6. So a equals negative 3, or a equals negative 15. And that's my answer. We talked about derivatives in the shapes of curves, how to find local max and min, global max and min, inflection points, areas where you're increasing, decreasing, concave up and concave down. We've also talked about family of functions, how to tell what the parameters do, to be able to do calculus on these things, and finally to find the values of the parameter. So thank you for listening. I tried to keep this short. And Monster Puppet, nope, you're not in this one. How can you do a video without a puppet? Lots of people do. We'll talk. All right. So anyway, so thank you very much for listening, and I hope you drive safe.